All right, so today what we're going to talk about is how to handle data that would be categorical. So we talked about having two major types of data, this idea of continuous data, which are things that would fall on those interval or ratio scales. We also had this other idea about data, which is where you have data that's categorical or discrete. Remember, the data that kind of falls into buckets. It's this or it's that. There's nothing in between, right? Like a continuum has things between. So if we talk about your weight, it's continuous. You can weigh 105 pounds to 270 pounds or whatever. And in between all those weights, though, there's additional weights. It can be subdivided infinitely. There's no space between. You don't just suddenly jump from 100 pounds to 172 pounds like they're groups. But if you think about something like eye color, ethnicity, type of car you drive, favorite television show, those things aren't on continuums. They're categories. You're either this or that. You either like Big Bang Theory or you like Frasier. You either like to drive an SUV or you drive a car. You either have blue eyes or you have brown eyes. You don't fall on some continuum in how we treat these data. And we haven't talked about how to handle that if you're trying to use it as an outcome or dependent variable. So far in our class, everything we've done has assumed that your outcome or your dependent variable can be measured on a continuum. And so now what do we do if we have something that is not that way, right? We learned how to use categorical things as predictors, like in an independent sample t-test where you have two groups, boys or girls. An ANOVA, where you could have multiple groups that you compare, such as different ethnicities. But what if you want to use something like gender or ethnicity as an outcome? There is an approach you can use, and there's several approaches to handling categorical data. A lot of times in these types of stats classes, they're not addressed as much because most of this is rooted in experimental tradition. And so what that means is if you can do an experiment, what you normally do is randomize people to groups, so your independent variable is groups, and then you measure some continuous outcome. Because if you can decide on your outcome, normally you don't want to know were they, successful or not. You want to know how successful were they on some scale, right? So if you think about like grades, if we use pass fail, that's categorical. If you use GPA points, that's continuous, right? So this is the kind of thing. A lot of times we use continuous outcomes when we design experiments because it allows for more variability, so there's more that can be explained. If there's only two possible outcomes, you might miss some additional information. So this is why these aren't all that common in areas that use a lot of experimental approaches. Nonetheless, it's important to be able to do such if you needed to. So let's talk about the major tests we're going to discuss, which are all chi-square tests. So chi-square or chi-squared, both terms are used. It is technically this Greek letter chi you see down here, and it is, yes, squared. So a lot of people throw a D on to chi-squared, but I just want you to know a lot of people also just write this as chi-square. It's the same thing here. I normally say chi-square. So the chi-square is a distribution. It's kind of like the F distribution. Actually, it's related to the Z distribution. So if you remember T, when you square T, you get the F distribution. Well, it turns out when you square Z, which we also learned about the Z or the normal distribution, when you square Z, you get the chi-square distribution. So it is kind of like the F distribution in many ways, and because of that, its shape is very similar. You can't have values less than 0. It's positively skewed. Larger values are more rare or more extreme. So a big chi-square statistic means there's something going on, something unexpected, right? And that's where we would then find significant results or reject the null. So chi-square allows us to take a look at predicting categorical outcomes. We're going to talk about two major branches of the chi-square test in this class, the goodness of fit test and the test of independence. Also, contingency tables are often used to refer to these types of tests. All right, so the first one is the goodness of fit test. And I want to start off by breaking it down into its pieces. How is it that we go about doing a goodness of fit test? And so here we go. We've got all the kind of stepping stones along the way. So the first thing you need to do is you need to identify the expected value. You do this by calculating the observed frequencies and then computing the expected values for your test. So Imagine we have some example. I know there was an example in the book in the past that we used that was 3 different types of beer. I mean, we could also say 3 different types of car. So say a car dealership is trying to decide whether a certain type of make of car is more preferable. And we're going to go very just glossier, like car, truck, SUV. Okay, I used an example like this in your homework, right? So say we've got a car, truck, and SUV, okay? And so if you've got these things, and then they tally up, okay, this month, how many sales did we have for these things? So notice what we're dealing with here are frequencies. So first, this is our variable. Our variable takes 3 levels, right? So here, we would say that K, which is the number of levels our variable takes, K here equals 3, because we have car 1, truck 2, SUV 3. So the number of levels of our variable is K, right? So that means our DF here is going to be 2 because it's 3 minus 1. So our DF term is 2, okay? So the variable here would be like type of vehicle. I'm going to abbreviate. It's too hard to write all this. So type of vehicle is our variable. It takes 3 levels or has 3 categories, right? Our variable has categories, so it's categorical data. And then what we're going to measure about our variable is going to be counts or frequencies. That's it. Because what else can you do? I mean, you can't average cars. What you do is you count cars, right? Oh, there were 12 cars that were sold. So say this last month they sold 12 cars, and say that they sold 3 trucks, and say that they sold 24 SUVs. Okay? So these are the frequencies, and we would call these the frequencies observed. They were what actually happened. So FO here, the frequencies observed, are the numbers of sales that actually occurred in the month. Okay? So what you would do now is you got to, okay, well, what would be my expected value? And a lot of times you can think of this, it's a function of your hypothesis. So the hypothesis is that there's no difference between the observed and the expected frequencies. And so your hypothesis here under the null would probably be that there is no difference in the rates at which these vehicle types sell, right? That would be the hypothesis. So what would we expect then? Well, we would expect them to all sell at equal rates. How can we figure that out? So how can we get the expected frequency right here? Okay, the expected frequency is N times P, where N is all of the counts, so you sum the counts, and P is the probability of that specific outcome or category occurring. So, say for example, we expected these to all sell equally. Well then P for each of these outcomes would be 0.33, right? Because we expect them to all occur 1/3 of the time. Okay, so P would be basically 1 out of 3, right? There's a 1 out of 3 chance that it's a car because there's only 3 types of things we're looking at, right? Okay, so what's our N? Well, we're going to get that by summing across. So we have 15 plus 24 . You need to pick a different color. That color is not very easy to read there. That color's better. Okay, so we have 39 is our N. Okay, because that's how many events or frequency things totally happen. So now what we would say is, okay, we expect 1/3 of 39 to be car, 1/3 of it to be truck, and 1/3 of it to be SUV. Okay, so what's 1/3 of 39? 1, 3, right, 13. So we would expect 13 cars, 13 trucks, and 13 SUVs. So notice the frequency observed and the frequency expected always have to sum to the same total because that's where they come from. So these would be what we call our FE values, our frequencies expected, right? This guy right here. So the frequency expected is how much you expected that thing to occur under the null hypothesis. The frequency observed is how much it actually happened. So here we have our data, and now what we would do is go through and actually compute this guy. This guy is the chi-square statistic. All right, that's how you do it. You get the sum of the frequencies observed minus expected squared over the frequencies expected. Okay, so we can do that for this example pretty quickly actually. So frequency observed minus expected. Observed 12, expected 13. So we have 12 minus 13 for that first one, right? We're going to square that, and we're going to divide by expected 13, right? So this is the first bit of this, right, for cars. So we've got to do it for all of them and sum them all. So we've got this one, we're going to do this one. So I'm going to just abbreviate here now. So what we would have here is -1 squared, which is 1. So we have 113. Everybody see that for car? So we've got 113, or we got 113 plus, then this next one we would have what? Observed 3 minus 13, 10 squared 100 over 13. Then we would have the last one, 11, right? Because observed 24 minus 13 is 11, squared is 121. So we got 121 over 13, right? And when we solve that and get the answer, that is going to be our chi-square statistic. So let's pull up Excel here, and we can do that real fast. All right. So if we do equals 1 divided by 13 plus 100 divided by 13 plus 121 divided by 13, we get 17.08. This is the chi-square statistic. All right, so that's chi-squared. We just did the whole test by hand, the whole thing, start to finish, right? We identified observed frequencies. We just said how many were sold to the dealership. We calculated the expected. We then solved for chi-square, and we get this answer. Now, we can get the significance of this answer in Excel. We could do other things, but if you go to chi-square distribution right tail, right, so this one right here, chi-square.dis.rt, right, and then you select your value of chi-square and your degrees of freedom, which we already got as 2, right? That is the p-value. So this says there's significant effect here. What does that mean? It means reject the null. These types of vehicles don't all sell equally. Some vehicles sell more than expected, right? So the interpretation here would be what? Well, let's just look at the data. There are technically follow-up tests. For our class and where we're at, we are not going to deal with trying to like do a bunch of follow-up binomial tests or whatever. We're gonna look at how do we interpret this, right, when we find the effect. So here we have 3 categories, and we're going to eyeball the differences. It's not the best practice if you go on to do additional research, but it will work for our purposes, all right? So how can we follow this up? All right, so if we look at cars, well, we expected 13, we had 12. That's not really all that different. Where do we see the differences in the table? The trucks and the SUVs, right? What we see is basically that there were 10 fewer trucks and 11 more SUVs. So what we would say is a chi-square goodness of fit test was performed to determine whether different types of vehicles sold at different rates. The test was statistically significant, and here's our chi-square information that we would report, right? And we would say the results indicate that trucks sold significantly less than expected and SUVs significantly more than expected. That's it. So that's the whole thing. That's how we go through the process. That's how we can do the math by hand. That's how we can interpret the results, right? And so this shows us not just an eyeball difference, but a real inferential difference that what we would infer is at this car dealership, right, SUVs sell more than you would expect and trucks less, right? That's the inference we're trying to draw here. Okay, so that is an example of the chi-square goodness of fit test. So let's move on and let's talk about the next one. All right, we already did an example. I often use examples in class that are supposed to be like fun participation examples, but for sake of time, I'm not going to use this right now. It's just a video from Matrix, right? Okay, so what we're going to do here is look at the test of independence. So this is really, really similar, okay? Very, very similar, but there's going to be more than one variable. So I'm going to use an example actually here, and this example we're going to use is from a video that I like.
But you decide this with rock, paper, scissors, lizards, fuck. What the fuck is that?
Rock, paper, scissors, lizard, Spock was created by internet pioneer Sam Cass as an improvement on the classic game Rock, Paper, Scissors. All hail Sam Cass. Hail.
How does it work?
Oh, it's very simple. Scissors cuts paper, paper covers rock. Rock crushes lizard, lizard poisons Spock. Spock smashes scissors, scissors decapitates lizard. Lizard eats paper, paper disproves Spock. Spock vaporizes rock, and as it always has, rock crushes scissors.
I'm sorry, can you repeat that?
Well, of course. Scissors cuts paper, paper covers rock. Rock crushes lizard, lizard poisons Spock. Spock smashes scissors, scissors decapitates lizard. Lizard eats paper, paper disproves Spock. Spock vaporizes rock, and as it always has, rock crushes scissors.
Almost got it. One more time?
Sure. Scissors cuts paper, paper covers rock. Rock crushes...
All right, so here we have an example that we could use. So we've got Sheldon and Larry, and Sheldon's proposing they're going to play rock, paper, scissors, lizard, Spock. So here we could do what's called a test of independence if they were to play, say, a bunch of rounds to determine whether or not there was a preference for a certain type. Now, this example is fun, but the issue we have if we actually use Sheldon and Larry is the data would be what we call related data. That is, Sheldon would have preferences that would be related within him. And so you'd be repeating observations on him. There is a way to do that. We're not going to learn it in our class. So we're going to just kind of generalize this to say whether or not, say, physics majors versus non-physics majors have different preferences, right? We'll say physicists. He's a physicist, right? So the way we could set this up, you've got physicists and you've got non-physicists, right? Okay, so what we have is a first variable here that takes two categories, which we could call the person or type of person, right? Okay, so there's one variable. So the thing is, what we're looking for in these types of tests is relationships between two variables that both are categorical. So there's one variable. Now we have another variable that can take up to 5 values. It's rock, paper, scissors, lizard, and Spock. Okay, so this is the play, essentially. What type of play the person makes, right? And there are 5 possibilities, all categorical. So what we could do now, say, is observe this game played a bunch. And if we watched a bunch of physicists and non-physicists play this game over and over, all these people being different people, so not the same physicist repeating. The idea is, right, that this data is independent. So imagine that you watch them play this all this time and you find these physicists and, you know, you get all the tallies and you find that, you know, physicists play rock, however many games you play, right? They play 3 rock, paper, 7, scissors, 10, lizard, 2, and Spock, 20. Right? Physicists are clearly going to play Spock more. Okay, so you get these outcomes, right? So here we had physicists play 30, 42 times, okay? Just adding together all of these things. Okay, so then you have the non-physicists that you watch play, right? And you see that they play rock, you know, 8 times. And the times you saw non-physicists play. They play paper 12 times. They play scissors 21 times. They play lizard 18 times. And they play Spock 7 times. All right, so I'm just making these numbers up, right? These numbers are just made up to illustrate an example, just made up. They would be the data you'd actually observe in the real world, right? This would be, I actually watch the game get played, and I tally all these things. All right, so now what we'd see is we got a total of what? 11 rock plays. We got a total of 19 paper plays. We got a total of 31 scissor plays. We got a total of 20 lizard plays. And we got a total of 27 Spock plays. We had 42 physicists play. And then we got 20, 41, 59, 66. So we've got 66 non-physicists play. Okay, so when we add all these, let's take this into Excel to speed up this process here for us, and we'll see how we can follow these steps. So construct the table. We made our table, right? Compute row and column totals. These are the row totals. These are the column totals, right? Then we got to calculate expected frequencies. Here, this is how we could calculate expected frequencies. Then we got to compute our statistic, all right? So let's take a look at these next steps, and we're going to use Excel to simplify this process. So we have the type of play, which is rock, paper, scissors, lizard, and Spock. We have the type of person, which is physicist or non-physicist. And then we have our data, 3, 7, 10, 2, and 20, and 8, 12, 21, 18, and 7. Now we'll check whether or not I did math well. We're going to sum all of these, right? And what this is going to do is give us our row totals like we did in our hand version. Okay, and here we're going to sum our columns, which is giving our column totals. All right, now, when you sum the row or the column, you're going to get the same number because it's the same data in the table. So if I sum the columns, this is going to be the total number in the table. But notice if I were to do that by summing the rows, I'll get that same number, right? So this is the total number in the table, 108. That's how many total observations there were here, all right? So what we want to know now, is there a difference in observed and expected? Now, I'm going to take this and make another table down here. And what we're going to do is paste all the values, and I'm going to remove, so I'm going to leave all the totals, and I'm going to remove the cell values. So this was our observed table. Now down here, we're going to get our expected table, and that is what would we have expected to happen if what? If physicists and non-physicists have no differences in the plays they make, okay? That's what we're asking. We're asking, is there a difference in which type of play physicists like to make compared to non-physicists? So, for example, are physicists playing Spock more than expected, but non-physicists are playing scissors more than expected, right? So you're asking, is there some difference in this or not? Okay, so we need to know what will we expect. How do we get the expectation? All right, so the expectation we see here is the row times the column for the respective the cell that we're looking at. So every cell has a row and column it belongs to. We'll look at that. And you divide it by the total. And that's going to get us our expected frequency for that cell. So what would this look like? All right. So this cell belongs to row 1 and it belongs to column 1. So what we're going to do, this times this divided by this. Okay? So notice what we got here. The row that it belongs to, the row total, the column total, divided by the total for the table. So we expected 4.28 rock plays in physicists. All right? And we're going to do the same process for all of these. So row times column divided by total. 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 All right, so what you got to do to get this to work, you don't have to do this, I just want to double check the values. Okay, I got to paste numbers only. And then when I sum all these, what should happen is I should get 42. There you go. All right, so this is now the sum of those, and it's still 42. So notice, the expected has to have the same totals, column and row, right? The question is whether or not those distributions between players or physicists and non-physicists is equal. All right, so we'll do the same thing here. Now we've got row, and we're now working on column 2, total. Row times column divided by total. Row times column divided by total. You're going to have this down. Row times divided by total. And row times column divided by total. So again, I'm going to take this I'm going to paste the values only. And then if we do our summation, there you go, we get 66. And the same thing now is if we sum these values are going to match the values here, right? So notice these totals all stay the same in your two tables. What changes is what's inside your cells. So is what the patterns you observed equivalent to the patterns that you expected? That's the question we're asking here, okay? So now this process becomes longer when you have bigger and bigger tables. So here we have 10 cells, right? 2 times 5, 10 cells. So we're going to have 10 of these terms to do, right? Does that make sense? So we got 10 terms to be able to solve for our chi-square value here. So if we were going to do that long way, what does that look like? So what we need to do is get the observed minus expected squared over expected. So it would be like this. Observed minus expected squared over expected, right? And so that one contributes that. And you've got to do that then for all of these. So this one is going to be those two. This one, those two. Those two. And this one, those two. So we see right now, like, the biggest contribution here is that physicist playing Spock thing. So then if we take this over, we can actually do this really fast. So now look at it, auto updates our references. So now we're doing rock to rock for our observed and expecteds. So now, if we get the sum of all of these things we just computed, that is chi-squared. And of course, we know we can get our p-value by using that value. And now we need degrees of freedom. So if you remember from our slide, we'll look at it again quickly here. Degrees of freedom is now k1 minus 1 times k2 minus 1. All right? How do we do that here? K is, again, the categories the variables can take. So we have 2 categories that our person can take, and we have 5 categories our play can take. So we have 2 minus 1, which is 1, and 5 minus 1, which is 4. 4 times 1 is 4. So we have 4 df in this. So there's our p-value. So this is a statistically significant result. And again, how would we interpret this result? Well, what we would want to do for our class purposes is take a look. Now, you could, say, for example, follow up and run a goodness of fit test for just the physicists or just the non-physicists, right? Because then you're just looking at, within non-physicists, is there a difference in the selections? Within physicists, is there a difference in the selections? So you could follow up with that. We're going to focus just on interpreting by comparing the observed to expected frequencies, which is just an eyeball difference. It's not the best way to do it, but it'll work for our purposes. So let's take a look. What we see here in the contributions of these tests. And so all I'm doing to get a sense of this is I'm looking at the contribution each of these cells is making. So remember, these are the contributions that are being made by the differences. This is physicist, this is non-physicist, this is rock, paper, scissors, lizard, Spock. And so these are just the pieces that I calculated to actually go into my chi-square. So these are the deviations squared over expected. So these tell us how much each of these differences contributes to the size of my chi-square value. So the bigger numbers in here are the ones that had more difference. So I see that these numbers are all very small. They're all sub 1. These numbers are very big. So what I can see here is that, and now I'm going to look, okay, this number is big. So I want to look in the table, and I want to compare the observed to the expected. And so here, for Spock, for example, these numbers are all relevant. So we see Spock in physicists made a big contribution. What contribution did it make? Well, the observed was 20, the expected was 10.5. So what I can see is that it was more than expected, right? Now, similarly, we see that there's a pretty decent contribution being made by lizard. Okay, so these ones go together. So, okay, what happened? Well, only 2 were actually played, and we expected almost 8. So it was less than expected. So we also see that these are mirrored in the differences we see in the non-physicist group, right? So if we look at the Spock observed expected for the non-physicists, we see that they played less than expected. And if we look at the lizard for the non-physicists, we see that they played that more than expected. So that's what we're focusing on for interpretation here. There you go. Okay, so hopefully that clarifies. That's how you could do this process, and we just went through all these steps together. All right, so we did our example using the fun thing. Now, there's a bunch of effect sizes, because remember, when you get a significant result, effect sizes help us to interpret that, to make more sense of it. So what you can do here, there's several types. We are going to focus on phi, Cramer's V. So phi and Cramer's V are useful. They are effect sizes that are kind of like an R square value, more or less. They can be between 0 and 1. Closer to 1, the greater the relationship. Closer to 0, the less the relationship. And so they're going to tell you how large a relationship is. Okay? You can get these automatically in programs, but the calculation here is pretty simple. You take the chi-square statistic you compute, and you divide by n times k minus 1. Now, technically, if you're doing phi, you won't see this k minus 1. Okay? But if you're doing Cramer's V, you will see the k minus 1. Now, here's the deal. If you always do k minus 1, you'll always get the right answer. In Cramer's V, the smaller of the row or column categories is your k. So in this case, we had a 2 by 5 table. So it would be 2 minus 1, because 2 is the smaller. So phi in Cramer's V would end up the same, because 2 minus 1 is 1, n times 1 is n. So if we do square root of chi-square over n, this would be our phi Cramer's V. And so that's a pretty strong relationship overall, right? And notice it's going to be between 0 or 1. If it's not, you did something wrong. So there you go. These are effect sizes. And again, they tell us how large a relationship is. That doesn't rely on the hypothesis testing, the effects of sample size, all those types of things. It's just how big is the relationship in some kind of practical sense. So for significant results, you'd normally want to report that calculation. All right, and so APA reporting, like normal, you would have the test statistic, degrees of freedom, the value, the p. And if it's significant, you should add the effect size. I have in our class example write-ups, so let me show you what I'm talking about. So in our files, you'll find the example write-up like this. And so here it was looking at computer preference and age group, right? So chi-square test of independence, so that's what we just did. We did a chi-square test. We would have chi-square with 4 degrees of freedom, right? And if we pick up our results here, so chi-square, it would be 4 degrees of freedom. Our chi-square value here would be 22.32. Our p-value would be less than 0.001. Our phi would be 0.45. These results indicate, what did ours indicate? That physicists played Spock more than expected, and Lizard less than expected, and non-physicists played Lizard more than expected and Spock less than expected, right? And notice here in the write-up, I gave those observed and expected frequencies to aid in interpretation. So this is the type of write-up you would use as a template or an example when you're trying to do your lab. Please be sure to look at this, consider what we've talked about to help you in reporting that more effectively. All right, and that is our lecture on chi-square.